So I would like to talk about statistical mechanics. That is my research interest. And in particular, I would like to explain how we can use probability theory to explain why matter suddenly changes behavior. Like a magnet, then as the temperature increases, loses its magnetization. I would like to first start with this example. So imagine flipping a fair coin, where our coin tosses, and we represent them with this variable x1, xn. So we have n coin tosses, and let's say that head is +1 and tails is -1. So each variable xi, so each coin toss, can be either -1 tail or +1 head.
Every probability theorist's favorite example.
Yeah, exactly. Exactly. So we can now compute the average, of course, so 1 over n, the sum from 1 to n of our xi. And one can ask, okay, but what does it change here? So what is the consequences when n is very big, so when n goes to infinity? We have this law in probability that is called the law of large number. That says that when n goes to infinity and we take an average, this goes to 0. So if we take a very huge samples, half of the coin tosses will be head and half of it will be tail. And what is
0?
Yeah, in this case, yes. Okay. What is very interesting, in my opinion, is that here the randomness that we have in our xi, that could be either -1 or +1, when we are taking the average and we are taking the limit for n that goes to infinity, it stabilizes because it goes to 0. And this is already a very powerful idea. However, we have that this randomness doesn't really disappear like magically. So if we take the average and we zoom in by multiplying for a proper scale, so square roots of n, then we have this other theorem in probability that I also mentioned in the interview. There is, of course, the central limit theorem. And this theorem says that the fluctuation of this term here, so I will write fluctuation, they behave like a Gaussian, so a curve of this type, like a bell curve, meaning that the sum of the xi will concentrate around 0, and with very high probability, it will take value from minus square roots of n and plus square roots of n. So we have the law of large number that tells us like where the average goes, and the central limit theorems how it wiggles around it.
Why is it square root of n exactly?
It comes from this zoom-in scale that we do. Okay. But then one can ask, okay, but what about rare events? So the law of large number and the central limit theorem, they are not saying anything. So what is the probability of having almost every head? In this setting, the law of the large deviation principle comes into play. So large.
So I would say if everything is heads and my coin is not fair.
Could be. But there are some cases when this happens. Yeah. And this large deviation principle says that the probability of rare events, so in this case that our average approaches m, where m, of course, it's our rare event, so it will be something like very different from 0, where 0 is the mean here. It decays exponentially, so this is something like a negative exponential of the form e to the power of minus n, this function I of m. So it decays exponentially in n, with a function. There is this, with a rate, there is this function that is called indeed rate function, and is a function that we can compute.
Ah, great.
So at this point, I would like to apply this tree theorem to this model of statistical mechanics that is called the Curie-Weiss model, and it's a model also for a magnet. So
was it found by Marie Curie or?
Yeah. So this was Pierre Curie and also Pierre Weiss.
Okay.
Here they have the same name. I think so. So let's suppose that we have our very schematic representation of a magnet. So we have this particle, and to each particle we assign a spin. There is sigma I. This spin can be either -1 or +1. So is -1 here if the magnetic moment is pointing down, and +1 when the magnetic moment is pointing up. Also in this case we can think about the average. So we define the magnetization. There is of course the average of the spin, and I will call it M. And since this is a physics model, then it's also described by its energy. We call the energy in this case Hamiltonian, and this sigma is called a configuration. It is nothing but a collection of n spins. And the shape of this Hamiltonian, the energy, is this one. So it's defined as -1 over 2n times the sum over all the I and the j of sigma I, sigma j.
So the M tells you whether magnets attract or repel each other?
No, this is just the average of the spin. So it's a thing that we define to study so we don't want to look only of the behavior of just one spin, but we want to look of the behavior of these things that is kind of the average of all our spins. And from this formula, we can notice that from this term, our model has a mean field approximation, meaning that each spin interacts with all the other terms, and this interaction is hidden in these terms. And also, we can notice that this energy is minimized when we have the spins here that are aligned. So if we have both spins that are +1 or -1, then the product is of course +1. And this whole term with the minus in front is of course negative.
So if it's +1 the product, then this tells you that they attract each other? Or they repel each other? Or can you
Yeah, I mean, this could be exactly, this is basically what happens, yeah. And we want to study the probability of a configuration.
Yeah.
And since this is a physical model, then of course we have that this probability has to respect this thermodynamic principle, saying that the configuration that are more probable are the one with the lowest energy. So our probability is something like e to the power of minus beta h of sigma, where beta here is the inverse of the temperature, and we are considering beta greater than 0.
Okay.
We already noticed that this form of the probability is very similar to the exponential that we have in the large deviation principle, and this is the key concept of this whole discussion. So thanks to this formula, we can also calculate the probability of a magnetization. That is actually the thing that we want to look at.
Okay.
And this magnetization is the probability of this magnetization is something like e to the power of minus n, this function phi beta of m, where this function phi beta is a function that we can actually compute, and it has two competing forces inside, because it's defined like this. So it's the entropy minus the energy, where the entropy is a force that prefers disorder, so prefers a magnetization that is equal to 0. So half plus 1 and half minus 1. While the energy is a force that prefers alignment, so a very large value of m. Now I should clean something maybe. Okay, so now that we have our function phi beta, this is a function that describes the behavior of all this model. And to study a bit deeper this function is better if we try to plot and to draw the graph of this function. So we notice that for, I will write here, for small value of beta, and in particular in this case of the Curie-Weiss model, the threshold is beta less or equal than 1, we have a graph of the function phi beta. There is something like this. So it's symmetric, and it has a single minimum in 0 for a 0 value of magnetization. And this means that the system is disordered and there is no spontaneous magnetization. While when beta becomes large, so for large value of beta, in particular for beta greater than 1, we are now in the low temperature regime because beta is the inverse of the temperature. So here is the high temperature regime and here is the low temperature regime. We have a graph. There is now still symmetric, but our minimum here splits into two minima. So we have a graph of this type. And we have a minimum here, there is minus m star, I will call it like this, and plus m star here.
That's symmetric.
Yeah.
Great.
And now the system has to decide either a negative magnetization or a positive magnetization. But in this case, the system has a magnetization. Yeah. So we go through the disorder case where our magnet loses its magnetization to this case where our magnet has magnetization. And this change of behavior of this function phi beta, this is the representation of phi beta, of course. This change of behaviors of the function phi beta, that of course reflects a change of the behavior of the models, in physics is called phase transition. And in this model we have that the phase transition here occurs for the critical value of the temperature, there is 1.
Can you say what temperature this is, or does it depend on?
Yeah, this is exactly the temperature. So.
So like how many degrees? Or
no, this one, no, exactly. Okay. This one, I mean, we are just taking the physical version of the temperature. So, yeah. So basically, to summarize everything we have done, we started with the law of large number that described the typical behavior of a system. And then we went through the central limit theorems that describe the fluctuation of our system. And then through the large deviation principle, we had a global shape of our probabilities. And when we apply the large deviation principle to an interacting particle model, for instance, the Curie-Weiss model, so a magnet, we find there is a very useful tool to study phase transition.
Great.
And that's it.
Thank you very much.
You're welcome.